Hello students, I am Rajiv Jha. I am going to explain my ninth video in series of question and answer on electrical machine. In this video, I am going to explain effect of load changes on a synchronous generator which is operating with standalone. So I hope you will like this video. So let's continue. So this is our topic, effect of load changes on a synchronous generator operating alone. The question is, what will happen if we increase the load on single operating generator? In my previous video, we talk about the synchronous generator and their connection with infinite bus system. So all the excitation we talk about in my previous video, we talk about the excitation and variation of excitation actually. So in that case are only valid for when alternator is connected with infinite bus system, but here we infinite bus system and that bus system is connected with load. So in the previous case alternator is not directly connected to the load. Okay, so in this case we talk about the synchronous generator operating alone. That means a synchronous generator, single synchronous generator connected directly to load. So in previous case, when we talk about the alternator is connected to infinite bus system, so the terminal voltage and frequency should be constant actually. But in this case, synchronous generator operating alone, there is no any compulsion of this. We will have to control uh, terminal voltage constant. So these are the different things. What happened when the load is changed, we will see in this video, and how we control the terminal voltage uh, by changing the you can say field resistance, or by changing the field current. So we will also see in detail actually. We will also see this method in detail. So let's start. So this is our generator and this is the load. So in this video we talk about load. Generator is directly connected with the load and that load is increasing. If that load is increasing, so there is some terms like load angle increases, load current increases, real oblique reactive power increases. So these things will be simultaneously increases when we increase the load on single generator. Okay, which is a load is connected with the single generator. So what will be the constant value? In my my previous video about the constant value, so this is the constant, this will be the constant. So here we also see the constant value is, yeah, this one, field resistance constant. When we talk about the single excitation or a single generator, yeah, standalone generator, operating generator, so with the load, in that case field resistors should be constant field current we assume. Third one is constant speed of prime mover. So here we say if should be constant, then if directly proportional to flux, so flux is also, or main flux is also constant. Okay, and then second one is constant speed of prime mover, omega. Okay, so omega is also constant here. So constant speed of prime mover here constant, and we assume constant prime mover, constant speed of prime mover and constant speed of field current. Okay, through this if we combine these effect, constant speed of field current, that means we have a constant flux, and constant speed of prime mover, that means we have a constant speed, omega, rotational speed. So we can say E is the EMF. So EMF generated in the alternator will also be constant here. So in my previous case, when the alternator is connected with infinite bus system, the EMF is not constant. E cos del is constant. Okay, but here directly EMF is constant. Okay, so the variations comes in the terminal voltage. We will see in the next slide. Okay, all the variation we will see in the next slide. So yeah, because we know the load is, there is a three type of load we have generally see. lagging power factor load, unity power factor load, leading power factor load. So first we will study for lagging power factor load. In lagging power factor load, what happened when load is increases? Okay, so in lagging power factor load, if we connect an alternator, single alternator, a lagging power factor load, so what happened when load is increased or load increases? Okay, load is increasing or load increases. So in that case, firstly we know in my previous slide you have seen EMF will be constant. So whatever the position, how it is constant, so whatever the position, EMF is only follow this arc, and the you can say the center of this arc is, or center of this circle is this one, and here you say this is the radius, and this arc EMF is follow. Okay, so the value of EMF, either this when we increase the load, and this and this, that means the value is changing, but the value of delta is changing, but the EMF value is constant, because in arc or in circle the radius is always constant. About their radius is always constant, whatever we take the in any point, in any point of the circumferences, the radius is constant. So here we say the EMF, this is the trajectory of the EMF, actually this is the trajectory of EMF. Okay, so first thing, if the load is increases, then what happened? So just here you see load is increases here. Okay, so load is increased, that means this is the first we have a load angle, then the load is increases, then we will get a new load angle. So the load angle is increases. So first thing, the load angle is increases, this is true. Second thing, terminal voltage. So terminal voltage, first we have terminal voltage V, then when the load is increases, so we will get a terminal voltage V dash. So terminal voltage is reduces here, so and which is significantly reduces actually. So here we say terminal voltage decreases significantly. Okay, we know what is voltage regulation. So voltage regulation is E minus Vt divided by Vt. Okay, into 100 if you talk about percentage in the form of percentage. So if the terminal voltage is decreased, or you can say the voltage regulation is inversely proportional to the terminal voltage. So terminal voltage will decrease significantly, that means voltage regulation will increases, or we have a large positive voltage regulation. Okay, so in this case you can say that voltage regulation will be large for the lagging power factor load. And if the lagging power factor load is connected and we increase the load, in that case voltage regulation is also increases more. Okay, so at the last we talk about the load current and armature current increases. So first of all, we know the equation of the generator E equal to V plus J XS IA. Okay, so here you see the value of JIA access, and here you see the value of JIA access. This value is large one. Okay, from this value, this is looking, this value is smaller and this value is large one. So the access is constant for both cases, that means there is a synchronous reactance is constant, so the change in the value is armature current or load current. So here we say the load current IA dash is more in case of the when we increase the load. Okay, so the new load current is also, or you can say the armature current is also increases. Okay, and the second way you understand this, actually E equal to V plus J IA access. Okay, so here you see the value of EV is constant, the value of terminal voltage we have seen, So we should have to increase the decreases actually, so we will have to increase this value. So that means the current should be increases. So through this way you can also justify your phasor diagram. Okay, because terminal voltage is decreases here, so that armature current should be increases because x is constant. Okay, so the next one is next power. Okay, here we talk about the lagging unity power factor load. If we connected a unity power factor load, in that case the constant, we know the E or the EMF should be constant here. Okay, this is the trajectory of the EMF. Okay, so in this case what happened when we increase the load for the unity power factor load? Unity power factor load means that angle between V and IA should be 0. Okay, you know well. So here you see, this is called this is the new EMF value, and you see the load angle will increases, and the current drop, or you can say the reactance drop is increases. That means the current is increases and the voltage is decreases. We will get the new terminal voltage which is decreases as compared to the previous one. Okay, from V it is decreases actually, but it is slightly decreases. Okay, in previous one you have seen, in previous case lagging power factor, you have seen the length of the decrease, or you can say that it is largely decreases from V to V dash, the gap is more. Okay, but in this case, but in this case one second, yeah, but in this case, okay, in this case we say the gap is small, so it is called the load angle is increases. That is the true. Okay, load angle is increases here, del dash is more as compared to del. Okay, then second one is terminal voltage decreases. Yes, terminal voltage decreases slightly. Yes, that true. So small positive voltage regulation, as we know voltage regulation is inversely proportional to terminal voltage. So if the terminal voltage slightly decreases, so voltage regulation or positive, we have a small positive voltage regulation. So try to remember this. Then the last one is load current and armature current increases. Yes, load current and armature current increases in this way. Okay, so the next one is, yes, leading power factor load. So in leading power factor load, the same thing, the EM constant. Okay, first thing is correct. First thing is same for any type of load. Then second one, we have seen here, this is the trajectory of EMF. Okay, so here we see, if we increase the load, so the first one we will have a load of this del value, then we increase the del dash, so the terminal voltage is increases. Okay, and armature current is also increases, terminal voltage is also increases. So in previous two case, unity power factor or lagging power factor load, the terminal voltage is decreases or it decreasing. Okay, but in leading power factor load, terminal voltage is increasing. Okay, so that is the difference actually. So you have seen, if load is increases, if load is increases, then load angle increases. Yes, load angle del dash is more as compared to del. Okay, then terminal voltage increases. Yes, terminal voltage V dash is more with V. Negative voltage regulation. Yes, terminal voltage, if the terminal voltage is greater than E, or you can say the EMF, in that case you have seen here the value of E dash is smaller than V dash, the value of EA is smaller than V. So the voltage regulation automatically, you can say the negative value, because voltage regulation is the value, you from the formula you have seen voltage regulation equal to E minus VT divided by VT. So the value of E is small and VT, the value of VT is more. So in that case, we will get a negative voltage regulation, and the negative voltage regulation we will have get, and here the V dash, the terminal voltage is increasing. So always it is negative in the leading power factor load. So generally in any we have seen in industry or any generating station also, substation also, we have generally used the lagging power factor load, or in case of ideal we have assumed that the load should be unity power factor load, but actually the load is lagging power factor load. We are not taking about 99.99% of load in our industry or any substations or any system is the lagging power factor load. Okay, so this is the true actually. So we are not dealing with the leading power factor load actually, but there is some load through which we will have to study leading power factor load and their variation. Okay, so if we increase the load, then this one is happened, and we will get the load angle increases, terminal voltage increases, negative voltage regulation, and load current is increases. That means load current is increases for any case. Okay, either you have either you go for the unity power factor or lagging power factor load. In both cases, in among of these three cases, the common is load angle, load current will be always will increases. Okay, will increase, and second one is load angle will increase. These are the common terms. The differences comes in the terms of terminal voltage. Okay, at unity power factor load, terminal voltage slightly increases, decreases, and in lagging power factor load significantly decreases terminal voltage, and in leading power factor load the terminal voltage increases. Okay, in terms of voltage regulation we have also got the differences. Okay, so the next one is, yes, so here you see if the load is changes in unity power factor load. If the load is increased, then terminal voltage slightly decrease. And the second one, the lagging power factor load, for the lagging power factor load, if the load is increases, then terminal voltage slightly decreases. For leading power factor load, terminal voltage, if the load is increases, the terminal voltage increases. So here we see the terminal voltage is varying. So it is desirable to keep terminal voltage constant to load, but here if load changes then terminal voltage affected. As we know, in any in any apparatus you have seen 220 volt, 440 volts. Okay, so these type of fixed voltage we want fixed terminal voltage, but here you see the terminal voltage is varying up if we vary the load. So because of this, so we will have to compensate this change, because we want constant load, we want constant load voltage. In that case we will have to compensate these changes. So how it is possible? So compensation is possible, or we compensate this variation of load through changing of EMF, because this, you know, this is the equation V equal to E minus IA XS. Okay, so if we want so initially we know we makes the constant EMF, but if we want to make the terminal voltage constant, in that case EMF should be varying. So EMF depend on E, directly proportional to flux, and omega is the speed of prime mover. So we through this way we can control the E, and if we control the E, we makes the terminal voltage constant. Okay, so E is directly proportional to phi into omega. So we have a two option: either we control by through the flux, or we control through the prime mover, speed of prime mover. So because in every load change of load, in every change of load, it is impossible to control the prime mover speed. So we have only option to control the flux. So flux is directly proportional to IF, that means field current, and field current is directly proportional to RF, that is the field resistance. So field resistance is a resistance which is connected with the field winding. Okay, so by varying field resistance we control the field current. Okay, we vary the field current, and so by varying the field current we know phi is directly proportional to if. So we control or we vary the flux. So by varying the flux we vary the ef, that means emf. So by varying the emf we can control the terminal voltage constant, or we can say we makes terminal voltage constant by varying the emf. So through this way we you can say makes the terminal voltage constant. That is our desirable you can say terms, which is which I want to desire for any. If we change any load, then the terminal voltage is always constant through changing the field resistance. Okay. So through this way we can in this video we have learned effect of load changes on a synchronous generator operating alone, and we also get to get to answer of that question, what happened when we increase the load on this generator. Okay, so I hope you like this video, and if you have any doubt, please mention on this on the comment box. I will definitely give you a answer. Okay, thank you.